In note 6.5 day 2, we're going to learn to graph secant and cosecant. We'll begin by building the parent functions, and then we'll graph general secant and cosecant functions. So remember that secant x is 1 over cosine x from the reciprocal identities, and cosecant x is 1 over sine x, and we can use these identities to help us build the graphs of the last two of the 6 trigonometric functions. We're going to begin by graphing cosecant x, and we're going to do that using the graph of sine x. So on the right here, I have a little table, and we're going to put some values for sine of x, and then cosecant will be those reciprocal values. So let's begin. So we know that sine of 0 is 0. Sine of pi over 6 is 1/2. Sine of pi over 2 is 1. And I'm getting these values from the unit circle. I can draw that in over here. So at this value, this is the point 1, 0. On my unit circle, pi over 6, this point is rad 3 over 2, 1/2. So that sine of pi over 6 is 1/2. Pi over 2 on the unit circle has the point 0, 1. Remember, sine is the y value, so sine of pi over 2 is 1. The next point that I wanted to look at was 5 pi over 6. I'm picking values that have sine values that have nice reciprocals. This point on the unit circle is negative rad 3 over 2, 1/2. So sine of 5 pi over 6 is 1/2. And sine of pi on the unit circle, this point is negative 1, 0. So sine of pi is 0. And now that we have these particular points, I'm going to find out what cosecant is. Remember, cosecant is the reciprocal of sine. So cosecant of 0 is 1 over 0, which is undefined. Cosecant of pi over 6 is going to be the reciprocal of 1/2. So that's going to be 2. Cosecant of pi over 2 is going to be the reciprocal of 1, which is 1. Cosecant of 5 pi over 6 is going to be the reciprocal of 1/2, which is 2. And cosecant of pi is going to be the reciprocal of 0, so 1 over 0, which is undefined. When graphing cosecant x, it's going to be helpful to first graph sine x. And going forward, when we do general cosecant functions, we'll also want to graph the corresponding reciprocal function. So I am going to graph y equals sine x. And if we recall how that works, I'm going to put, I'll put a scale on the axes because we need that. So I need one on the y-axis. So 1 unit I'll do is 1 square. Okay, and now I'm going to go ahead and put the graph of sine x on my graph. So I have a point at the origin, 0, 0. Then we have a maximum at pi over 2, 1. Goes back through its own axis at pi 0. Then 3 pi over 2, negative 1. And then continue on with the pattern, having a key point every quarter period, which is every pi over 2 units. So this is the graph of y equals sine x. Now, when we graph cosecant, we have to remember that cosecant's the reciprocal of sine. And because of that, we know that whenever sine x is 0, cosecant x is undefined, and that means cosecant x will have a vertical asymptote whenever sine x is equal to 0. So I am going to draw in vertical asymptotes every time the graph of sine x crosses through the x-axis. And when we do transform functions, the vertical asymptotes will occur whenever sine x crosses its own axis of oscillation. So we have vertical asymptotes here at x equals 0, x equals pi, x equals 2 pi, x equals 3 pi, x equals negative pi. Okay, those are the vertical asymptotes. And now let's plot a few points. So I'm going to show you, this is pi over 6 is 2/3 of the way into the first square, and 5 pi over 6 is 1/3 of the way into the last square before pi. So now we're going to plot some points on cosecant x. So we had the point pi over 6, 2. So let's plot that. Pi over 6, 2. Then we had the point pi over 2, 1. So pi over 2, 1. And then we have the point 5 pi over 6, 2. So 5 pi over 6, 2. And then I'm going to connect these with a nice smooth curve. And I know that my graph will approach those vertical asymptotes but never touch them. And I'll get a U-shaped curve of this type. It's not a parabola, but it is U-shaped. And if we think about going into the next section between pi and 2 pi, we know that at 3 pi over 2, cosecant will be -1 because sine is -1 there. And then thinking about the vertical asymptotes, I know that the graph will approach these vertical asymptotes but never touch them, and I'm going to get another U-shaped curve that's going downward there. If I go into the interval between 2 pi and 3 pi, I have the point 5 pi over 2, 1. And then it's going to be a U-shaped curve going up. And then I can go into the interval between 0 and -pi, and I can graph another branch. I'm going to highlight one cycle. So one cycle for cosecant needs to include one full upward section and one full downward section. So what I've just highlighted here is one cycle. And now we are ready to do the characteristics. Okay, so let's scroll up a bit. So the domain here, just like tangent and cotangent, is not all real numbers because we have vertical asymptotes. So the domain is going to be all real numbers, except we need to exclude values where we have the vertical asymptotes. So x is not equal to, and if we look at our vertical asymptotes, they were at 0, pi, 2 pi, 3 pi. So x is not equal to n pi, where n is an integer. Okay, the range is going to be all y values. So if we start at -infinity, we see we have all those values, -infinity, up until -1. So that's going to be the first part of our range. So our range is going to be -infinity to -1 inclusive. But then when we get to -1, between -1 and 1, we don't have any values. And then beginning from 1 all the way up to +infinity, those values are part of the range. So we're going to have -infinity to -1 inclusive, union, square bracket, 1 to infinity. That's the range. The period is how long does it take to complete one full cycle. We highlighted one cycle already, and that takes from 0 to 2 pi. So the period is going to be 2 pi, and if we change the period, we need to have a horizontal dilation, and this makes sense. The period is the same as the reciprocal function, which is y equals sine x, right? It makes sense that it has the same period. X-intercepts, where does this graph cross the x-axis? So this is cosecant, I'm highlighting it, and here's the x-axis. So we actually have no x-intercepts, so there are none. Vertical asymptotes, we've already talked about those. They're going to be x equals n pi, where n is an integer. Okay, local maxima points. So local maxima are the highest points in an interval. So local maxima point, I'm circling these. We have 2 on our graph. So I'm going to write down the order pairs, and then we need to express this in a general equation. So the local maxima we see are pi, -pi over 2, -1, and then we have 3 pi over 2, -1. And to get from one to the next, we're adding a full period, which is 2 pi. So if we want to write a general expression, I would pick one value. So let's say I pick 3 pi over 2, and then I need to add an integer multiple of 2 pi. So plus 2 pi n, comma -1, where n is an integer. That's an expression for all local maxima. Local minima are the lowest points in an interval. So local minima points are here. So this is a local minimum, and this is a local maximum. So let's list a couple local minima. So I have pi over 2, 1, and I have 5 pi over 2, 1. To get from one to the next, I'm adding 2 pi, so a full period. And if I want to write a general expression, I pick one value, pi over 2, and then I have to add 2 pi n. The y-coordinate's still 1, where n is an element of the integers. Okay, is this function odd or even? If it's even, it has y-axis symmetry. If it's odd, it has origin symmetry. So we can see that this function is odd. The point pi over 2, 1 is on the graph. So is negative pi over 2, -1. Change the sign of both x and y. So this function is odd because it has origin symmetry. So it's odd just like sine.